All right, let's talk about something that is just completely wild when you first hear it. Orbital mechanics. It's this whole area of spaceflight where pretty much everything you think you know about motion gets flipped completely on its head.
Okay, so think about this. On Earth, if you want to catch up to the car in front of you, what do? You step on the gas, right? Simple. But what if I told you that in space, doing the exact same thing, hitting the accelerator, will actually make you fall further behind? It sounds crazy, I know. So let's figure out what's going on here.
So, to get to the bottom of this weird paradox, we need to talk about the fundamentals. We have to understand the energy of an orbit and the invisible forces that are always at play up there. Really, it's all about a constant tug of war between speed and gravity.
So first things first, what is an orbit? You know, it's not just about being super high up. It's really this delicate dance. You've got gravity, that blue arrow, always pulling you towards Earth, but you also have this incredible forward velocity, the red arrow, that's trying to fling you out into space. When those two forces are in perfect balance, you end up constantly falling, but you're moving so fast sideways that you just keep missing the planet. You just fall around it. It's a state of continuous free fall. And yeah, you gotta be high enough so that air resistance isn't a factor.
Okay, so every single thing in an orbit, whether it's a satellite or a whole space station, has what you can think of as an energy budget. Physicists call this mechanical energy, and this budget is made up of two types of currency. Kinetic energy, which is just the energy you have from moving fast, and potential energy, which is the energy you have stored up just by being high up, by having that altitude. And the key thing is, these two are always being traded back and forth.
And here's a great way to think about it. A roller coaster, right? When you're at the very bottom of a big drop, you're flying. That's max kinetic energy, max speed. But then as you start climbing that next huge hill, you slow way down. What's happening? You're trading your speed for height. You're cashing in your kinetic energy for potential energy. And in orbit, it works in the exact same way.
And this is super important because almost no orbit is a perfect circle. They're usually ovals or ellipses. That means a spacecraft is always doing that roller coaster trade-off. It has a high point, called the apogee, where it's furthest from Earth and moving at its slowest. That's the top of the roller coaster hill. And then it has a low point, the perigee, where it swings in close and picks up a ton of speed. That's the bottom of the drop.
Okay, so we've got the energy balance down, but how do you actually change your path? How does a pilot steer this thing? Well, it's all about firing your engines, but the way you fire them is everything. Basically, it boils down to two key maneuvers. You've got your prograde burn. That's when you fire your engines behind you in the direction you came from to add speed. Think of it as hitting the gas. Then you have the retrograde burn. That's when you fire your engines in front of you in the direction you're headed. It acts like a brake, subtracting speed.
Let's look at that prograde burn first. So you hit the gas. Instantly, you've added kinetic energy. Now your spacecraft has more oomph, more forward momentum, so it starts to fight back against gravity's pull a little harder. And here's the crazy part. The result isn't just that you go faster right now. The result is that you start to climb, and you actually raise the altitude of your orbit on the other side of the Earth.
And you guessed it, a retrograde burn is the mirror image. You fire the engines to slow down, which kills some of your kinetic energy. Now gravity has the advantage. It starts winning that tug of war, and it pulls you in a little tighter. This makes the orbit on the far side of the planet get lower.
All right, we've got all the pieces now. We know about kinetic and potential energy, and we know about prograde and retrograde burns. So let's go back to that original question and finally solve this rendezvous puzzle. Okay, put yourself in the cockpit. You're piloting a SpaceX Dragon capsule. Your target? The International Space Station. It's on the exact same orbital path, just a bit ahead of you. You need to catch up and dock. What do?
So your gut reaction, your Earth brain, says, easy, I'm behind, so I need to go faster. You light up the engines for a prograde burn to pick up speed. I mean, it makes perfect sense, right? But in space, your intuition can be your worst enemy. And this is where it all goes wrong. Remember what a prograde burn does? It adds kinetic energy, yes, but that pushes you into a higher orbit. It's the roller coaster again. You just traded speed for altitude. Now you're on a bigger, longer orbital track, and a longer track takes more time to go around. So your average speed is now slower than the ISS. You'll actually float up above the space station and watch it get even further away from you. You lose the race. Okay, so hitting the gas was a total fail. What's left? Well, you have to do the one thing that feels completely backward. You have to hit the brakes.
That's right. The winning move here is to perform a retrograde burn. You actually fire your engines to slow yourself down on purpose. So how on earth does this work? Well, by hitting the brakes, the retrograde burn, you're removing kinetic energy. This lets gravity win a little, and it pulls you down into a lower orbit. A lower orbit is a shorter track. It's a smaller circle. And because you're on this shorter, faster track, your average speed around the Earth is now actually higher than the ISS. You'll drop below the station, sure, but now you're finally catching up. So you see, a real rendezvous is this beautiful two-step dance. First, you hit the brakes, retrograde burn, to drop into that lower, faster orbit. You ride the inside lane basically to catch up. Then at the exact right moment, just as you come up from underneath the space station, you hit the gas, a prograde burn. That pushes you back up, matching the ISS's altitude and speed perfectly so you can dock. It's incredible.